More than 2,000 kilometers beneath the Pacific Ocean, a vast flow of liquid metal changed direction. Scientists did not see it directly. No drill can reach Earth's outer core, and no camera can survive anywhere close to it. Instead, researchers reconstructed the movement from nearly 3 decades of measurements of Earth's magnetic field collected by ground observatories and satellites. The result was unexpected. Before about 2010, a broad flow of molten material beneath the equatorial Pacific moved weakly westward. Then it changed. By around 2012, the same region had developed a strong eastward flow. The motion intensified for years, peaked around 2020, and has since begun weakening again. This does not mean Earth's entire core suddenly reversed rotation. It does not mean the magnetic poles are about to flip. What changed was a large regional circulation pattern inside the liquid outer core. And that distinction is important, because this moving metal is part of the engine that creates Earth's magnetic field. Earth is built in layers. At the surface is the crust. Beneath it lies the mantle, a vast region of hot rock extending almost 2,900 kilometers downward. Below the mantle is the outer core. Unlike the solid rock above it, the outer core is liquid, composed mainly of molten iron with nickel and lighter elements mixed in. It surrounds the solid inner core and reaches temperatures of several thousand degrees Celsius. The liquid is constantly moving. Heat escaping from deeper regions drives convection. Earth's rotation organizes some of that motion. Differences in composition and density add further complexity. Because molten iron conducts electricity, moving it through an existing magnetic field generates electric currents. Those currents produce more magnetic field. This self-sustaining process is called the geodynamo. It is responsible for most of the magnetic field surrounding our planet. That field reaches far beyond Earth's surface. A compass aligns with it. Satellites use models of it. Navigation systems account for its gradual changes. And farther into space, the magnetic field helps create the magnetosphere, which interacts with charged particles arriving from the Sun. But Earth's magnetic field is not fixed. Its strength and direction slowly change over years and decades. Scientists call this secular variation. If researchers can measure those changes accurately enough, they can work backward and estimate how the electrically conducting liquid in the outer core must be moving. It is like watching ripples at the surface of a hidden river and reconstructing the current below. The new analysis used geomagnetic measurements spanning 1997 to 2025. It combined information from observatories on the ground with satellite observations, including measurements from ESA's SWARM mission. SWARM consists of satellites designed to measure Earth's magnetic field with extremely high precision. But there is a problem. The magnetic signal measured by a satellite does not come only from the core. Magnetized rocks in Earth's crust contribute. Electric currents in the ionosphere contribute. The magnetosphere contributes. Even the oceans produce weak magnetic signals as salty water moves through Earth's field. Researchers must separate these components before they can isolate the slower changes associated with the core. Once that is done, they can create maps showing how the magnetic field evolves over time and use physical models to infer the flow at the top of the outer core. The new reconstruction revealed several large-scale features that remained fairly stable, but beneath the Pacific, one region behaved very differently. Around 2010, the inferred motion changed from weak westward flow to much stronger eastward flow. To picture the scale, imagine an enormous river of liquid metal flowing horizontally thousands of kilometers beneath Earth's surface. The movement is slow by everyday standards, but the mass involved is extraordinary. This is not a narrow stream. It is part of a planet-sized circulation system. A relatively small change in flow speed or direction can alter how magnetic field lines are stretched, transported, and concentrated at the boundary between the core and mantle. That is exactly what researchers are trying to understand. The Pacific reversal appears to be connected with sudden changes detected in Earth's magnetic field. One of those occurred in 2017. Scientists call such events geomagnetic jerks. Despite the name, they are not violent physical jolts of the planet. A geomagnetic jerk is a relatively abrupt change in the rate at which the magnetic field is evolving. Imagine driving a car whose steering wheel has been turning slowly to the left. A geomagnetic jerk is not the car instantly turning right. It is more like the rate of steering suddenly changing. These events have been detected several times during the satellite era. The 2017 jerk was especially noticeable in the Pacific region, and the new analysis links it with changes in flow inside the outer core. Why the deep flow reversed remains uncertain. One possibility involves interactions between different layers inside Earth. The solid inner core does not simply sit motionless inside the outer core. It rotates, exchanges heat with the surrounding liquid, and may interact mechanically and electromagnetically with it. Variations near the inner core boundary could influence patterns farther outward. Another possibility involves waves moving through the liquid core. The outer core is not just convecting randomly. Rotation and magnetic forces can support large-scale waves and oscillations. These may redistribute angular momentum and change circulation patterns over years or decades. The reversal beneath the Pacific could therefore be part of a natural oscillation rather than a one-time event. That possibility becomes more interesting because the flow strengthened until about 2020 and has since begun weakening. If the trend continues, researchers may eventually see the circulation return toward its earlier state. That would suggest a cycle, but the available record is too short to know. Modern satellite measurements cover only a few decades. Earth's core has been operating for billions of years. Trying to identify a long-term pattern from 30 years of data is like watching a few seconds of a machine and trying to determine its full operating cycle. This is one reason the discovery matters. Earlier models often emphasized relatively stable, large-scale core circulation, especially strong patterns beneath the Atlantic Hemisphere, and weaker flow under much of the Pacific. The new results suggest that some regions can reorganize more rapidly than expected. Earth's deep interior may therefore be more variable on decadal timescales than many simplified pictures imply. The Pacific is particularly interesting because the magnetic field above this region has shown unusual behavior in several data sets. Changes there can propagate outward into global magnetic field models. These models are not purely academic. Navigation systems, directional drilling, satellites, aviation, and scientific instruments all rely on knowing the orientation and strength of Earth's magnetic field accurately. Because the field changes, those models must be updated. The more scientists understand the motions producing the changes, the better they can forecast how the field may evolve. However, this discovery should not be confused with a magnetic pole reversal. Earth's magnetic field has completely reversed polarity many times in geological history. During a full reversal, magnetic north and south eventually switch places. The last major reversal occurred hundreds of thousands of years ago. The Pacific flow reversal is something entirely different. It is a change in the direction of molten iron movement within one region of the outer core. Regional flows can change without triggering a global magnetic reversal. There is currently no evidence from this study that Earth is entering one. The same applies to dramatic claims about Earth's rotation. Moving fluid in the core can exchange angular momentum with the mantle, and scientists study links between core motion and tiny changes in the length of the day. But the reversal identified beneath the Pacific is not causing Earth to suddenly spin backward or change its rotation in any noticeable way. Its importance lies in what it tells us about a place we cannot directly visit. Humans have sent spacecraft beyond the solar system's major planets. We have landed machines on Mars. We have collected samples from asteroids. Yet Earth's outer core remains inaccessible. The deepest boreholes penetrate only a tiny fraction of the distance toward it. Almost everything scientists know about the deep interior comes indirectly from earthquake waves, gravity, laboratory experiments, and the magnetic field. That makes satellite observations unusually powerful. A spacecraft hundreds of kilometers above Earth can detect subtle magnetic changes caused by liquid metal flowing thousands of kilometers below its surface. The two regions never physically touch. The information travels through the magnetic field connecting them. The new analysis effectively turns that field into a window. What scientists saw through it was not a perfectly steady geodynamo. They saw motion capable of reorganizing over little more than a decade. A weak westward flow beneath the Pacific changed into a strong eastward flow. That eastward circulation intensified. A geomagnetic jerk appeared. Then the flow began weakening again. The next question is whether it will continue fading, reverse once more, or evolve into an entirely different pattern. ESA's swarm satellites and future magnetic missions should allow researchers to keep watching. Every additional year extends a record that is still extremely short compared with the timescale of the core. Eventually, scientists may discover whether the Pacific event belongs to a repeating cycle, a deeper interaction with the inner core, or a type of instability that has not yet been fully understood. For now, the discovery changes one simple picture of our planet. Earth may look solid beneath our feet, but at its center is an ocean of metal. And that hidden ocean is moving, reorganizing, and continuously rebuilding the magnetic field around us.